Question 3, part 2 asks, what is the critical angle at the interface for the velocities given in problem 1, and what is the critical distance if the layer thickness is 5 kilometers? So I've drawn the diagram from problem 1 here. We have an incoming wave going up through the ocean bottom into the water. The velocity of the ocean water is 1.5 kilometers per second, that's VP1. The velocity of the ocean sediment, VP2, equals 3 kilometers per second. And the thickness of that second layer is going to be 5 kilometers. That's going to become important when we're talking about critical distance. But for now, we're just focusing on these numbers, VP1, VP2, and we're going to try to figure out what the critical incident angle is. And to do that, we need to first know what our critical refracted angle is. So let's define what a critical angle is, right? The critical angle is the incident angle at which no transmitted energy is radiated into the second layer. So we have to ask ourselves, well, at what angle do we have to draw the transmitted P wave, the refracted P wave, so that none of that energy is traveling into the second layer from the point of incidence? So we can see here from the point of incidence, where are we going to draw this refracted wave so that none of the energy is traveling into the second media? Well, we can see that our only option here is drawing it perfectly parallel to that interface, or 90 degrees from the vertical, right? If we have an incoming wave, it hits this at some I critical angle, it's going to hit this point of incidence, and it's going to refract at that interface, and it's not going to travel into the second media until, of course, it's traveled the critical distance, x crit. So right there, we've drawn a vector that is not going into the ocean water. That is going to be our critically refracted wave. So let's go on to use Snell's law to figure out what this critical angle is, right? The critical angle is the incident angle for which the refraction angle is equal to 90 degrees, right? So we can draw this, I've already drawn it here, this little angle sign. I critical, or critical angle, is going to be that critical incidence angle for which we see this vector right here, this refracted wave that travels 90 degrees at parallel to the interface. So let's go back to Snell's law. We see Snell's law here, V1 over V2 equals sine I over sine R. Or for a critically refracted wave, V1 over V2 is equal to sine I critical divided by sine R critical. We already know that R critical, right, the critically refracted wave, has to be traveling at 90 degrees. So now we have V1, V2, and we have R, or in this case R critical. We have 3 parameters for 4 unknowns. We can plug and chug at this point and find out what I critical is. So this equation is going to become V1 over V2 equals sine I critical divided by sine of 90, right? 90 is our angle at which none of the energy is transmitted. That's our critically refractive angle. Sine of 90 degrees is, of course, equal to just 1, so this simplifies to sine of I critical equals V1 over V2. Easy. So let's go on and solve this equation. We know that sine I critical is V1 over V2. We can take the inverse sine and figure out what I critical is, right? So that equation is equivalent to I critical equals sine to the negative 1, or inverse sine, of V1 divided by V2. Just simple math at this point, right? V1 equals 1.5 kilometers per second. V2 equals 3 kilometers per second. You'll notice that 1.5 is exactly 1/2 of 3. So this will simplify to I critical equals the inverse sine of 1/2. Make sense? Right. So if you want to take your calculators at this point and plug that in, inverse sine of 1/2. If you have a graphing calculator, you'll do that by going up to the top left corner, or top left corner, you see the green button with a little diamond on it. That's the third function. Push the green diamond, then push wherever your sine button is. In my case, it is Y, so that plugs in inverse sine. And then you just put in parentheses 1/2, and it returns 30 degrees. Right? It's a pretty basic trigonometric value. So we now have our critical angle. I crit equals, in this case, 30 degrees. That is the angle for which the wave is going to be critically refracted parallel to the surface. But we're not quite done yet because we still need to find out what the critical distance is. And that is where we're going to pull in that first value from before, h1. There's also a trigonometric function. If you want to go back in your textbooks, they might have derived it. I think more likely they probably just gave you this equation. Once you've figured out the critical distance, and there is a way to figure out critical distance without first knowing critical angle. If you just use Snell's law and some basic trigonometric relations, cosine squared, sine squared rules, you can actually find out if you're given velocities what your critical distance is going to be. But it's a much simpler equation if we already have our critical angle, right? So the critical distance is the distance x that the critically refracted wave must travel along the interface before it can be detected at the surface. And this distance, by definition, is x crit, the critical distance, x, equals 2 times the height of the originating material. In this case, we're given 5 kilometers. That's the thickness of the material from which the wave is coming. 2 times h1 times the tangent of the critical angle of incidence, I crit. We've already solved for I crit before, right? Cool. So it's a pretty simple equation, right? We already have I crit. We can just plug and chug at this point, given h1, which is going to be equal to 5 kilometers, and the critical distance x becomes 2 times 5 kilometers times the tangent of 30 degrees. Tangent of 30 degrees is root 3 over 3 times root 3 over 3. I'm not that good anymore. Calculate it real quick. 10 times root 3 over 3 is 5.77 kilometers, right? So this works out to a critical distance x equal to approximately 5.77 kilometers. I don't know what she expects for you for sig figs. You could say 5.8, you could say about 6 kilometers, what have you. But that is our critical distance. So part 2 is done.